This lesson deals with a piecewise linear model for a BJT. You can find these notes in the ECE302 ebook in Chapter 3, starting on page 16. So as that we take the VI characteristics of our NPN and our PNP transistor and just straighten them out. So here's our diode between the base and the emitter, and we'll call this voltage VBE on. And this is when the collector emitter is greater than or equal to 0. This is the first quadrant behavior relative to our actual curve. And then when we're in the third quadrant, we have a base collector that gets forward biased, and I'll use an R subscript here to indicate that that's a turn-on voltage for the forward biasing of that PN junction. Likewise, let's take the characteristics in this first quadrant and straighten them out. So a straight line here, and then straight lines coming this way. This voltage we'll call V sub CE sat, and the relationship between I sub B and I sub C is beta F. So in other words, for an IB3, I'd have a beta F IB3. Do the same thing in the third quadrant. Straighten the line out. Again, have different values of base current. Call this voltage V sub CE reverse sat. And then I labeled the value here as minus beta R plus 1 IB3. Let me just derive that. Beta R is the ratio of minus E to I sub B. So let's cross multiply by that. And then I sub E is equal to I sub C plus I sub B. Let's take this and put this on this side of the equation. That'll give me a minus I sub B and beta R I sub B, and then put this on the other side of the equation as a plus I sub C. The current I sub C is equal to minus beta R plus 1 I sub B. We saw that in an example in our previous lecture, where we had a value here of minus 80 microamps for a value of 40 microamps here. Remember, this is a plotting of I sub C and not I sub E. And we get the same results here for the PNP, except that the subscripts are reversed. So this would be the emitter base turn-on voltage. This would be the collector base reverse turn-on voltage. Of course, we change the direction of all of the base and collector currents. Here we change the subscripting here from collector emitter to emitter collector. Let's start out by modeling the active region. This is where we forward bias the base emitter and we reverse bias the base collector. What are all the things that are true when you're in the active region? Let me go back to the previous page, page 16, and show you where I got these numbers or inequalities from. If we're in the active region, we're somewhere along this line. That's saying that VBE equals VBE on, and the current is greater than or equal to 0. Let's take a look at this first quadrant here. If we're in the active region, we're along these lines, and that says that the collector emitter voltage is greater than or equal to VCE sat. The collector current is positive, in other words, greater than or equal to 0, and the ratio of I sub C to I sub B is beta F. Let's go back to page 17. These are all the conditions that we observed to be in the active region. Can we make up a model that covers all of these? Well, the answer is no, we can't. And the reason is that we're going to take a guess, put our model in, and then check to see whether the model's been contradicted or not. So we can't satisfy all of these conditions because some of them will be violated when we put in the wrong model, just like we did for the diode. This first term here, VB equals VB on, sounds like a battery between the base and the emitter. And then here's the collector current as a multiple of the base current. That sounds like a current-controlled current source between the collector and the emitter. I'm able to realize this condition and this condition. This model covers more than the conditions that are here. In other words, the current in the base can be positive or negative, but it can only be positive for a BJT. Likewise here, the voltage across the collector emitter is the voltage across a current source, and that can be positive or negative. I need to check that this is true. If the base current is greater than or equal to 0, the collector current will be greater than or equal to 0 because it's a multiple of the base current by beta F. If we assume that this model is the correct region, then we're going to analyze the circuit and we're going to have to check that I sub B is greater than or equal to 0 and that VCE is greater than or equal to VCE sat. For the PNP model, we really have the same things. We just have subscript changes. We've also changed the direction of all the currents. Now what I did here was I drew the model upside down. In electronics, we show schematics where the current flows from the top of the drawing to the bottom. So you might see an NPN transistor drawn this way because current's going to flow in this direction. For a PNP, they usually draw the emitter on the top because current's going to flow in this direction. Let me draw the model by reversing the direction of these two sources, my voltage source and my current-controlled current source, but then draw it upside down. Show the emitter here, and so I have a voltage between the emitter and the base versus the base and the emitter, and I have current flowing into the emitter and out of the collector, where the collector current is beta FIB. Here too, this model covers more than my actual constraints are up here. I'm going to need to check that I sub B is greater than or equal to 0, and now that V sub EC is greater than or equal to V sub EC sat. This is all written out on the bottom of this page. Let's model saturation next. This is where we forward bias the base emitter junction and forward bias the base collector junction. Now, what are all the things that are true when you're in saturation? I've listed them here, but let's again go back to page 16 and see where those came from. To be in saturation, we're along this line, VBE equals VBE on, and the current in the base is greater than or equal to 0. If we're in that saturation region, we're along this line. In other words, we would be along here for a given value of base current, and then when you go active, you go this way, you turn the corner. If we're in saturation for a value of IB2, we're along this line, but saturation is over here. The collector emitter voltage is equal to VCE sat, the collector current is greater than or equal to 0, and the ratio of I sub C to I sub B is actually less than or equal to beta F. In other words, when you're on this line here, I sub C is equal to beta FIB. But when you're over here, it's a little bit smaller. Let's go back to page 18. Those are all the things we just pointed to. Now again, can I build a model that does this? No, but I can come pretty close. This is saying that the voltage between the base and the emitter is a battery. Put a battery there. And this is also saying the same thing, that the collector emitter voltage looks like a battery of VCE sat. Now this model covers more than the constraints that are here. In other words, the current in a voltage source can be positive or negative or 0. I'll have to check for this condition. Likewise here, this current in this battery can be positive or negative or 0, so I need to check that it's greater than or equal to 0. And lastly, the ratio of these currents, I can't guarantee, so I have to check that the ratio of IC to IB is less than or equal to beta F. For the PNP, flip the model around, show the emitter on the top and the base and collector on the bottom. I'm reversing the direction of this voltage source, now between the emitter and the base, and then this voltage source between the emitter and the collector. We need to check that I sub B is greater than or equal to 0, I sub C is greater than or equal to 0, and that the ratio of IC to IB is less than or equal to beta F. And all this is at the bottom of the page. Let's model cutoff next. This is where we reverse bias the base emitter junction and reverse bias the base collector junction. Now, what are all the things that are true when you're in cutoff? Well, again, let's go back to page 16 and find these conditions. So to be in cutoff, we're operating along here. The base current is 0, and the base emitter voltage is less than or equal to VBE on. We're operating along this line over here in cutoff. The collector current is 0. And the collector emitter voltage is greater than or equal to 0. Let's go back to page 19. Those are all the things that we observed on the drawing. Can you build a model to cover all these? Again, no, but I can cover quite a few of them. No base current and no collector current sounds like an open circuit. The voltage across an open circuit can be positive or negative. This model, again, covers more than what I need constraint here. So I need to check that the base emitter voltage is less than or equal to VBE on if we were to assume that this was the model. And then likewise, the voltage across this open circuit can be positive or negative, but I need to check that it's greater than or equal to 0. For the PNP, same model, but now our currents are in the opposite direction, although they're still equal to 0. I will still need to check the voltage now between the emitter base, that's less than or equal to the emitter base turn-on voltage. I have to check that the voltage between the emitter and the collector is greater than or equal to 0. Our assume state techniques. We assume a model, analyze the model in the circuit, and then do the checks. These are shown at the bottom of each of the pages describing the models. Just like the diode, we have transition points. One I'm going to call the edge of saturation. This is where the active and the saturation regions overlap. We take our two models. They both had that VBE equals VBE on. They both had that I sub B was greater than or equal to 0. They both had that I sub C was greater than or equal to 0. But to be in the active, we had greater than or equal to, and in saturation, we had equal to. So we're just going to take the intersection of those two. For the active, we had that I sub C was equal to beta FIB, and then to be in saturation, it was less than or equal to. Can we build a model that covers all these conditions? Again, no. This is a battery between the base and the emitter. This is a battery between the collector and the emitter. But now I have to constrain the current. There is no element that you can specify the voltage and current of except a resistor. and that won't work here. So I'm just going to label the current as beta FIB. Now we still have to do checks. We have to check that I sub B is greater than or equal to 0. But if that's true because of this equation, this will be true. Only one thing needs to be checked. So if we were assuming that we're at the edge of saturation, we'd put this model in and then do this check. The same thing for the PNP. Everything reversed. Here's our battery between the emitter base and the emitter collector. And then we'll label the current coming out of the collector as beta FIB. And then check that I sub B is greater than or equal to 0. All of this is described below. Our other transition point I'm going to call the edge of cutoff. This is going to be the overlapping of the active and the cutoff models. To be in the active region, the base emitter is equal to VBE on, but to be in cutoff, it's less than or equal to. We'll take the intersection of those two as equal. The base current is greater than or equal to 0 for active and equal to 0 for cutoff, so we'll take that intersection. The collector emitter needs to be greater than 0 for cutoff and greater than or equal to V sub CE sat to be inactive, so we'll grab that as our intersection. And the collector current is beta FIB in the active region, but if the base current is 0, then the collector current is equal to 0. Can we model this completely? No, but we can come pretty close. No current is an open circuit. This is a battery, but that battery has no current, so I have to label it. We've covered everything here. We've covered this, we've covered this, we've covered this. We need to check that this is true. Same for the PNP, just reverse all the directions and do the same check. This is at the bottom of the page. Our next modeling is in the inverse mode, but before I do that, let me go back to page 16 and just show you where the edge of saturation and edge of cutoff are. The edge of saturation is right here, where the active and the saturation models intersect, and the edge of cutoff is right over here. Let's go back to page 22. There are also models for inverse active, inverse saturated, inverse cutoff, as well as the edge of saturation and edge of cutoff in the inverse state. The models basically are replacing beta F by beta R. V sub BE on is replaced by V sub BCR on. V sub CE sat is replaced by V sub CER sat. And for the PNP, listed those over here. These are pretty rare, and I'll do some examples in the supplemental problem sets in case you ever run into this case. And these are piecewise linear models for a BJT.